I created the sampling distribution of the mean differences by using a few lines of code which ran in a statistical software, and a computer did the job in a few milliseconds. But in the days of Gosset, Fisher, and Pearson, there were no computers. Or in fact, they were computers, but the computers were humans who were doing calculations by hand. So I'm sure that Gosset had better things to do than to do this repetitive job. Perhaps tasting the products of the company he was working with. So, what Gosset and Fisher and others did was to create probability distributions. And with these probability distributions, they created tables that indicated what is the probability of observing values within some interval. And they published those tables. So statistical researchers who were not statistically savvy, they were able to use these tables to conduct their research and find out what was the probability of observing the results they observed if the null hypothesis was true. So, the other important thing was that these distributions had to have some generality. It shouldn't be useful only for one type of measurement. So in my sampling distribution, I used the values that were expected to find in the height of the plants I used. But what about if we have to deal with milliseconds or kilograms, and the values are much higher or much lower? So we need some distribution that deals with some sort of standardized values. That's what Gosset did. He created a distribution that today is called the t-distribution, or more specifically, the student's t-distribution. That distribution is this distribution of a t-score. The t-score has this general form: data, some statistics of the data, minus a parameter in the population of the null hypothesis, divided by sampling error. So let's see how we translate that into the specific case of the study of different types of barley. So the statistic of the sample is the mean difference. So we calculate the mean of the values for type A, and we calculate the mean for values of type B, and we obtain the difference between these two values, minus the mean difference in population of H0. Well, what's the difference in means if in the population, the hypothetical population in which the null hypothesis is true? Well, that mean is 0. And then we have to divide that by the estimated sampling error. What's this? Well, remember the sampling distribution I created. The standard deviation of a sampling distribution is called standard error. So, basically it's the standard deviation of that distribution. Now, there is a way of estimating that value, the sampling error, using the values of the sample. So let's continue, and we replace this by the numbers we obtain in our sample. So remember, when we obtain the difference between the mean of values of type A and the values of type B, the difference was 13.25. Minus 0, which is the mean of the population in which the null hypothesis is true. So now we need to find the estimated sampling error of mean difference, which is the standard deviation in the sampling distribution I created. Now, there is a formula which we can use to obtain that, which is the square root of the combined variance divided by the number of values in sample 1 plus the combined variance divided by the number of values in sample 2. Now, the number of values is easy. It was 8 in each sample. But what's the combined variance? Well, the combined variance is the sum of squares of sample 1 plus the sum of squares in sample 2 divided by the degrees of freedom of sample 1 and the degrees of freedom in sample 2. Now, what's the sum of squares? Well, remember when I calculated the variance and the standard deviation, I subtracted the mean from each of the 8 values of each sample, and then I squared those values. And then I obtained the sum of those squares. Well, that's the sum of squares of 1. And I did the same with the 8 values of sample 2. So this is the sum of squares of 2. Now, what's degrees of freedom of 1 and degrees of freedom of 2? Well, degrees of freedom in this case is the number of observations minus 1. Why minus 1? Well, when you calculate a mean in a sample, then one value is not free anymore. So you can change the values of, if you want to obtain the same mean, you are free to vary 7 values. But let's say you choose different values for each of these 7 values. Now the last one, if you want to obtain a specific mean, that value is not fixed anymore. It's not free anymore. You need to fix it to some specific value to obtain the mean you wanted to obtain. And the same happens with the sample 2, because you calculate a mean in sample 2 as well. So therefore, that would be 7 in each case. So let's replace those numbers. So the sum of squares in type A was 86.87, and the sum of squares in type B was 109.87. And the degrees of freedom, as I mentioned, 7 in each case. Now we plug that now we have to plug this combined variance number in the formula, and then we are going to replace N1, which is the number of observations in sample 1, with 8, and N2 with 8 as well. Okay, so this value now is going to be there. So the combined variance was 1405, has to go there and there, and the value of 8 was replaced there. So what's the square root of all this? And so now we do 13.25 minus 0, which is obviously 13.25, and now we have to obtain the square root of all these values, and is 1.874. So the t-score is 13.25 divided by 1.874, and that equals to 7.07. That's the t-score that describes our sample. Now, the t distribution is the one that we are going to use to compare our value 7.07. How likely is to obtain this value or a more extreme value in the t-distribution? But here we use it with measurements that are obtained from plants of barley. But we can use the t-distribution with many types of measurement, provided that they are numerical. So here is the t-distribution, which has the mean of, it is centered around 0, and the distribution depends on the degrees of freedom. So in this case, this is a t-distribution with 14 degrees of freedom. Remember that we have 16 values, but we lost 2 degrees of freedom when we calculated 2 means. So the shape of the t-distribution changes with the number of degrees of freedom. For the degrees of freedom 14 has this shape, and we try to locate a t-value of 7.07 in this distribution, and obtaining the t of 7.07 or more. But we have to consider the two extremes, because we don't have a directional hypothesis in which we say we expected A to be better than B. And so because we don't have a directional hypothesis, we have to look at the two sides, two tails of the distribution. So we need to look at 7.07 or more and negative 7.07 or less. What's the probability? Well, we can see that it's very low, because we already have 99%, and it's even more than 99% of the distribution is in this interval. So the probability of obtaining a t-score of 7.07 or more extreme in a t-distribution with degrees of freedom 14 is 0.00000056. That is, the p-value is 0.00000056. And sometimes we just say the probability, the p-value is less than 0.001. Now, if our threshold our significance threshold as proposed by Fisher was 0.05 or even 0.01 or even 0.001, then we reject the null hypothesis. So we say that the mean difference that we obtain in our sample does not come from a population in which the null hypothesis is true.